So far, we have looked at pre-sheaves and sheaves of modules that were defined from modules over each open set. So we had this M of U and we required this to glue nicely. One special kind of such constructions that one might think about is that, okay, if I have an affine scheme, so if X is spec of R, then I have a ring R in the background, so I can take M an R module. Now this M, can it give me a sheaf of modules so that I somehow on open sets define its localizations, whatever this means, and this will give me a sheaf? And the answer is yes, and we will look at that now. But before we start, we need to understand what it means to localize a module. So we have seen localizations of rings, and it turns out that modules can be localized in exactly the same way. So more precisely, if R is a unital commutative ring, and you take a multiplicatively closed subset S in R and an R module M, then the module M over R gives rise to a module over the localized ring S inverse R. This is given by base change that we have seen before in these lectures, where simply you tensor M over R by the ring S inverse R, and so you get a module over S inverse R, and this is called the localization of M at the multiplicatively closed set S and denoted S inverse M. If you don't like this base change, there is an explicit construction that is very analogous to that of localization of rings. Namely, on M times S, you consider the equivalence relation that is analogous to that of rings, namely that for some U in S, U acting on ms prime minus m prime s is 0. Then calling the equivalence classes M divided by S and putting an S inverse R module structure on them as follows. So addition of two such classes is defined in the usual way, and the action of the ring S inverse R on S inverse M is defined in this multiplicative way. Then this gives you a module structure, and this will be exactly the module S inverse M. So as for rings, when we localize at a multiplicatively closed set consisting of powers of some element, we denote the localized module by M sub A. And when we localize with respect to the set S, that is everything except the contents of a prime ideal, we write M sub P. And localization behaves well with respect to all reasonable constructions you might think of, such as direct sums, exact sequences, and so on. So now let's start our enterprise to define a sheaf starting with a module. So we want to make an R module, M, into a sheaf of modules over spec R, where the stalks of this sheaf are the localizations of M at the points. And remember, the points of spec R are precisely the prime ideals of R. So we let X be the affine scheme spec R and take an R module M. Then we define the sheaf M tilde as follows. So for each open U in X, M tilde of U is the set of all phi p with p in U, so that each phi p is in MP. And for all p in U, in a neighborhood around p, phi is equal to the quotient g divided by f for some g in R and f in M. So let's take a moment to see what this is. This is analogous indeed to the definition of the structure sheaf, but now instead of taking things in R, we take them in M. So this condition says that phi is equal to g divided by f in a neighborhood of P. And remember, g divided by f, this is an element of the localization of the module at the prime ideal Q, demanding that f is not in Q. So this whole thing makes sense. And basically, we have defined this m tilde by specifying its stalks. And it turns out that this construct, m tilde, defined in this way, is indeed a sheaf of modules on X, and it's called the sheaf associated to the module M. And what I said earlier is the statement that R tilde is exactly the structure sheaf, because it was defined in exactly the same way. But one has to observe a few things. So this really just defines R tilde as a sheaf of modules. So R, the ring R, and sheaves of rings in general have multiplication, of course, but here we don't have multiplication inside the module, we have multiplication with elements in R. And so this is worth noting that when we say that it is a sheaf of modules, we need to specify how the ring R, or how the OX of U acts on M tilde of U. But OX of U, these are just elements, say psi p. And so to get it to act on our phi p, well, on the level of stalks, this is exactly so. An element psi p is of the form R divided by S, because the structure sheaf was exactly defined in this way. So locally around each point, an element of this sheaf is of the form quotient of something in R by something outside the prime ideal, and it acts on GF by RG divided by SF. Of course, I could have summarized all this by saying in the only reasonable way, but this gives you some explicit description. And if you want, you can pause and go back to the lecture where the structure sheaf was defined and check that this is indeed the case. These sheaves associated to modules have some nice properties. So here I have some bad notation where P denotes an R module and a point in X at the same time. Please bear with me, they will not occur in one and the same line. So for each point in X, the stalk of M at this point is the localization at P. Second, for each F in R, the section of M tilde at the principal open subset UF is exactly the localization of M at F. The proof of these is verbatimly analogous to the proof of the case M equals R that was hinted at when we defined the structure sheaf of scheme. As a special case, if you take the principal open subset U1, that is the whole scheme X, then this is the localization of M at 1, which is exactly M. So M is the global section of this sheaf. So the sheaf really takes localizations of M at open sets, and globally it is just M. Further properties: morphisms between M tilde and N tilde for two R modules, M and N, correspond bijectively to module homomorphisms. In one direction, if I have f from M tilde to N tilde, then I get a morphism for each open set, in particular a morphism of global sections from M tilde of x to N tilde of x, but this is just M and this is just N. Conversely, if I have G from M to N, then I can localize and so I get, say, GA from principal open subset, or from localization at A. And gluing together from the principal open subsets UA, I get something defined everywhere. And these two constructions are inverse to each other. Another property is that if you have an exact sequence or a sequence of modules, it is exact if and only if the corresponding sequence of sheaves of modules is exact. This can be proved locally using two properties. First property is that a sequence of modules is exact if and only if it is exact after localization at all prime ideals. And a sheaf, as we have, so this first is a fact from commutative algebra, and we glossed over without proving that a sheaf is exact if and only if it is exact, or a sequence of sheaves is exact if and only if it is exact on the level of stalks. But from the first property, since the stalks are exactly the localizations at prime ideals, these two are the same thing, so therefore the exactness is equivalent. And one can show that this construction commutes with tensor products, duals, and direct sums. So the sheaf associated to the direct sum is the direct sum of the sheaves associated to M and N. The sheaf associated to the tensor product is the direct sum of the tensor product sheaf of the associated module. So remember, this is the sheafification of the naive tensor product. And the fact that this holds testifies to the fact that sheafification is the right concept. And the same goes with dual modules. The specific proofs of these statements are not very revolutionary and do not add much understanding, which is why I am omitting them. If you're interested, you can take any one of these properties and try to prove it yourself as an exercise. So there is a name for sheaves that come from this construction. So we had one direction saying that given a module over R, we associate to it a sheaf. But given a sheaf, you can ask, does it come from such a module or not? If it does, then you call it quasi-coherent. More precisely and more generally, you can define this for any scheme X. namely a sheaf of modules over X, is called quasi-coherent if there is an open cover of X, so that the restriction of this sheaf to any affine open set, so you have this affine open cover, and you require the restriction to any affine open set to be the sheaf associated to some module over the ring Ri. Quasi-coherent sounds like it comes from a notion of coherence, and indeed you can call a sheaf coherent if in addition these Mi are finitely generated modules over Ri. In practice this will very often be the case, but nevertheless one speaks more often of quasi-coherent sheaves than coherent sheaves, even in the finitely generated set. One can show that the restriction of a quasi-coherent sheaf to any affine open set is of the form M tilde. So in particular, if the scheme is affine from the beginning, then the quasi-coherent sheaves are precisely those of the form M tilde for some R module M. And kernels, images, quotients, direct sums, tensor products, and duals of quasi-coherent sheaves are quasi-coherent. This follows from the properties listed in the previous slide, because there we realized exactly these things in terms of their constituents. So for example, we did the tensor product, we did exact sequences that cover kernels, images, and quotients, we did direct sums and duals. So in the affine case, the previous slide shows exactly that not only is, say, the kernel of the map quasi-coherent, but you should see exactly what it is. And by gluing this, you get the same result for a general scheme. Also, there are examples of non-quasi-coherent sheaves of modules. One small example is the following. So we take as X the affine scheme spec of the polynomial ring localized at T. Then the points are the prime ideal generated by T, that's a closed point, and the prime ideal generated by 0, that's a generic point. And so the open sets are precisely the scheme itself, the empty set, and the set U, which is X without the closed points. So it's the set of the generic point. So the generic point is open. So let us make up a sheaf by hand, so to speak. So we set f of x and f of empty set to be trivial, and f of u to be the module localized at the 0 ideal, which is exactly the section at u. And as restriction maps, so I'm defining a sheaf by hand, so as restriction maps I set the 0 maps. Now, this is a sheaf. There is not really much to check. There is not much gluing going on. And it is clearly a sheaf of modules, and the fact that the restriction maps are 0 makes everything work. But this section at U is non-trivial. So if it were quasi-coherent, it would have to come from a non-zero module. At the same time, f of x is trivial. So if this were quasi-coherent, then the global section would have to be our non-trivial module. And this is a contradiction, so not all sheaves are quasi-coherent sheaves.